G'day there. Welcome to the third in our series on solar and battery training. Today we're going to be looking at system configurations, particularly for hybrid, solar and battery on grid, and understanding the difference between AC coupled and DC coupled. Let's get into it. Okay, so we're right at the start of today. Welcome everyone. Really excited by the number of attendees who come to these webinars. Myself being in lockdown, along with Rachel, who I'll introduce in a moment, we basically are making the most of being at home and trying to share some knowledge around solar and battery storage systems. So just to introduce Rachel, actually is part of the team here at Solar Plus. Normally, Rachel is on the end of a phone giving support to our customers. Rachel's experience as an electrician means she understands the trials and tribulations of installers and designers and can give you great support. So say hi, Rachel.
Hello, everyone. Welcome.
And if you hear any bangs or screams in the background, it's probably either my house or Rachel's. We both got our kids here at home, so a bit of homeschooling going on in the background. So we're looking at off-grid solar and battery systems. Now, yesterday we talked about hybrid solar and battery systems, and what I mean by hybrid is on-grid with a solar PV system and storage. So it's a bit of a marketing term. Some of you who might be from an international area outside of Australia and New Zealand might use that term differently. Technically, it generally means multiple AC sources, but within the context of this presentation, hybrids on-grid with solar and batteries. I'm now moving on to off-grid with solar and batteries. One of the things I like to say about the difference between on-grid and off-grid is the difference is getting smaller and smaller. People's expectations of storage are becoming very similar, whether they're on-grid or off-grid. For instance, people expect that if you've got a battery, you have backup. It's not always the case, though. As we learnt yesterday, some hybrid systems are only for self-use of solar. If the grid goes off, then you have no power. In the case of off-grid systems, of course, it's got to supply continuous power. So the focus today will be around system configurations, and then we'll probably move on to some more specific information about battery systems in general. So, off-grid systems. Incidentally, all of these slides which you're seeing right now, I put in the description below the YouTube video. So when the YouTube video is published later today, you can also download these slides. And you're welcome to share them and use them as you wish. They're for training and education. Now, this is my kind of very simple single line diagram of a typical off-grid system that's configured in what's known as AC coupling. Now, yesterday we talked about AC coupling and DC coupling. I'm going to focus on AC coupling here, mainly because it's becoming very, very popular, certainly in Australia and New Zealand, because it scales very well for off-grid. You'll notice that I've got some color coding here, brown as in non-renewable energy, green as in battery storage, and yellow as in solar sourced energy. And the load center, which is basically a switchboard where you connect all those components, can use all three forms of energy in different mixes based on the programming of that system. The purpose of a generating set is to provide a guaranteed backup. Now, any system that relies on the sun, there's always the possibility you don't have enough sun. Your load energy exceeds what your requirements are, and you'd basically empty your battery in the middle of the night, perhaps, and the power goes off. So having a generator set is a very good idea, but it's not mandatory. I mean, if you're prepared to experience blackout conditions occasionally because of overuse, you may choose not to have a gen set. Now, what I've seen in the industry over time, and I've been doing this for like 30 years now, is people are starting to move to off-grid systems without a backup generator. It seems to be a little bit risky, but the cost investment in that generator compared with investing in just more and more renewables is a valid argument. So oversizing a PV system so that it produces way more than you need, so even under the worst conditions, it's still going to meet your requirements, is one of those design options. But there is a problem. with this arrangement. Now, yesterday we talked about how something special about an AC coupled inverter is that it's capable of sharing energy between the solar inverter. So over here, the solar inverter. The solar inverter can output AC power, and I've drawn this as three-phase, but it could be single-phase, doesn't really matter. That power will first supply the loads. Surplus power will flow in the reverse direction into the load side of this battery inverter. Now, not all inverters can accept power on their load output. So don't assume this is the case. To my mistake, I tried this once without thinking about it, and the smoke did in fact come out of the inverter. So you've got to make sure the inverter is designed for reverse power flow and be able to charge batteries with that. So in this diagram, we've got an inverter that it's bidirectional on its load port. Energy can flow from the solar inverter to the battery inverter and charge the battery. So that's called AC coupling. The advantage of this is these AC solar inverters generally are very cost effective, certainly as you scale up in size, and they operate at relatively high string voltages. So it's possible to use conventional stringing arrangements of, running a single phase inverter at 400 or 500 volts DC makes for very easy arrangement of panels, and in three phase even higher. The sizing of these two, the battery inverter and the solar inverter, are somewhat locked together though. You have to consider that if you've got 10 kilowatts of solar inverter power here, this battery inverter needs to be able to accept 10 kilowatts or in some way curtail it. Because if it can't accept the full power of that solar inverter, you're going to basically damage that battery inverter. So that's a design consideration based on the product that you're using. So we've had a few questions come in. Rachel, what have we got?
Yeah, Glenn, Jonathan had a sort of questions. You may have covered them in your first webinar, which I missed, and it's kind of ties in with designing an off-grid system about the optimum angle of the panels. So Jonathan says, we've been taught to put them at the best angle for total annual production. But over the years, he's noticed winter's the time we need it, and energy in summer we've got enough.
Okay, good question, Jonathan. Look, if you'd asked me this 10 or 15 years ago, I'd say face them to the equator, which in the southern hemisphere is north. Tilt them at an angle that gives the best performance when the load to solar ratio is at its worst. Now, for a residential system in southern Australia and New Zealand, that typically means wintertime. The days are short. The energy use is often either slightly higher, and therefore the PV input is way less. So in Victoria, for instance, where I live, in winter we get 1/3 as much solar radiation on average in winter as we do in summer. So we would typically 10 or 15 years ago optimize the installation angle of the panels to suit that ratio. And so that might mean you're putting your panels up at 50 or 60 degrees incline. So they really stick up high. But what's happened since then is the cost of panels has come down tremendously, irrespective of any government rebates that we're lucky to have in some countries. The cost of panels have come down, but the cost of mounting systems haven't dramatically dropped. And so there's a valid argument now that actually, rather than spending money on tilting panels to the optimum angle, you spend the same amount of money on more panels to achieve the same outcome. So tilt angle is a variable. You may just choose to, for aesthetic reason and for wind load, to have the panels parallel to the surface of the roof because it's easier and cheaper to install it that way. But there's another consideration, which is the ratio of when the energy is used. Not so much ratio, but the load profile of the installation. Now, for a residential system, you may find that there is quite a high load early in the morning and late in the afternoon. And so you may actually get a better match of your solar production to your load's requirements by orientating that array in two directions, east and west. Once again, I wouldn't have done this 10 or 15 years ago, but now with a lower cost of PV, a little bit of oversizing and a little bit of mix and match of your array angles can give you a better self-consumption of solar. Now, the advantage of directly consuming the solar energy rather than storing it in your battery for later use is that that's the most efficient way to use solar PV is directly consume it. Because if you put it into a battery, you're going to lose maybe 5% as it goes through the inverter and charges the battery, and another 5% as it comes back out again. So you're losing 10% of your energy by putting it in and out of the battery. And plus there's the battery losses on top of that. So any more questions there, Rachel?
We're good for now, I think.
Okay. So
someone suggested, sorry, I missed their name, that rule of thumb is latitude plus 15 degrees, but you don't have to stick with that.
Yeah, I agree with you, Rachel. Rules of thumb are based on solar geometry, which is that latitude angle is approximately the average angle that the incline of a panel would be to match the average production over the whole year. And tilting it another 15 degrees biases it a little bit towards a winter cycle. But like I said, there's many more factors now, such as cost, aesthetics, and direct matching of loads. So I wouldn't be too hung up on it. Really the aesthetics is becoming more and more of an issue as systems get bigger, putting a lot of tilted panels on an array on a roof. But then again, if you're doing a ground mount system, you choose the angle. There is no roof. So that's when, optimum angle probably is sensible because you're building the whole structure from scratch. Okay.
Can I quote or misquote you?
Go for it.
Did you say, I think I've heard you say that our south is better than Germany's north. Our south is better than Germany's south.
I know what you're saying, and I think I said it wrong the first time too. I'm just there is a kind of a little bit of a misnomer, or not a misnomer, a misconception amongst a lot of installers. It's somehow, if you live in the Southern Hemisphere and if you live somewhere like New Zealand or Southern Australia, that putting panels on the south side of a roof, which for those of you on the Northern Hemisphere is the shadier side of a roof, doesn't make sense, is illegal, won't work. Well, actually, it's all about latitude and solar resource. And if you look at the raw numbers for a location like Victoria, which is not that sunny by Australian standards, actually a south-facing roof, the performance over the year is better than an optimal facing roof in Germany. I'll say it again. So a south-facing roof in Melbourne is better than an optimal facing array in Germany. So actually, it's about your location. Germany is latitude like 50 to 55 degrees from the equator, where in Victoria, we're 37 degrees from the equator. So it makes a big difference how far from the equator you are. The closer you are to the equator, the longer the sun is above you at a higher angle. And apart from cloud cover, generally your yield will be greater anyway. How are we going there? Have we filled those questions out yet?
There's a couple of more just popped in. There's one from David Skelton. I'll let you answer this. Any idea why the CER requires the battery inverter on an off-grid system to be on the approved list to receive STCs? CEC? You mean CEC?
Okay, so that's probably a little bit of a niche Australian question. CER, Clean Energy Regulator. STCs is our incentive program in Australia, small-scale technology certificates. And it's a kind of a lazy way of confirming that inverter system is suitable for installation in Australia. If you're not creating STCs, that's not an issue. So if you're doing megawatt scale systems, you don't have to be on the CEC list. Let's just say it's a local perversion of how things are approved. There's still perfectly good inverters that aren't on that list. So I see Matt has chimed in here as well. So he's asking a question about, based on your experience, and given that AS4086 is over 15 years, now that's the old battery standard for lead acid, nickel iron, and nickel cadmium batteries, would you say the design principles outlined in the standard are still important, and do you believe they should be reviewed? Actually, they are being reviewed. We have actually updated some of the related standards to 486 in Australia. It is actually used in New Zealand, even though it's not a joint standard. But since the new battery standard was published, 5139, 4086 was retired. But its sort of sister standards, 2676, 3011, have been updated. And the principles in them are good. And we will actually be covering some of those in this series, which is the principles of calculating ventilation, for instance, where there is explosive gases. So I'll move back to the presentation at this moment, and we'll come back to questions in a little bit. But thank you for those questions. That was great. We were looking at this diagram here and talking a bit about an AC coupled off-grid system and some of the considerations with an AC coupled system and managing energy flow within that. So just to reiterate here that an AC coupled system allows you to share energy from a generating source that's renewable, so that's the PV over here, through an AC network, which is the blue lines, back to a battery storage system. The coupling is through an AC bus, AC cables, a switchboard. The advantages of this are many, and you can, for instance, have them in different locations. You don't have to co-locate your equipment. For instance, let's say you're on a rural property and you've got a shed out the back, which is where you want to put the batteries because they're space hungry and you don't really want to have them in your lounge room, nor are you allowed to anymore in Australia and New Zealand. You might want to put them in that back shed, but the back shed is covered with trees all around it and shady and cool, which is actually quite good for most batteries, is to be shady and cool, but it's no good for solar. But there is a submain that goes out to that back shed. So the solar inverter could be on the main house where the sun is shining and it can generate efficiently without shade. And so the energy can flow across that submain to the back shed. So no co-location, it's a bit of a plus. You can add multiple solar inverters. They don't have to be one. You could actually have more than one, as long as there is some communication system that allows them to be controlled. So just to point out why there is a control system required. If you've not got a grid connection, so this is off-grid, there's nowhere for surplus energy from the solar to go. It can't spill anywhere. So you really need to consider how do you curtail, which is reduce the output of that solar inverter. When the batteries are full, the loads are light, you just don't need the energy. And that's generally done by two strategies. The older strategy was using what's called frequency shift power control, invented some 20-something years ago, I think by SMA, which was the battery inverter would deliberately slightly change the frequency. Very small, just a 1.5 hertz maximum variation. And that frequency shift was a way of communicating to compatible solar inverters that they must reduce their power output. Now, we talked about this in earlier webinars, that solar inverters actually control the array. So you don't have to worry that your array's got 10 kilowatts of PV connected. The inverter determines how much of that will be converted into AC power. It doesn't have to be spilled anywhere. It just doesn't get produced. So when that communication's occurring, the battery inverter is shifting the frequency. It's basically telling the solar inverter, reduce your output to X, reduce it by 50% or reduce it by 80%. And that way it can control the charge rate for the battery. Now that's historically the oldest way of controlling across an AC network. A more modern way, and probably a bit more faster, which is in terms of having a very fine-grained control over your solar inverter, is a comms cable. So some systems, they have a communication cable between the battery inverter and the solar inverter and use that to tell the solar inverter what its power output should be. And we're talking like, a few milliseconds, it will respond. And that's quite important because, when when a sun pops out from behind a cloud, it's instantaneous power. It needs to respond quickly, that inverter. It can't just sort of, oh yeah, we'll get around to it eventually. So those two methods, frequency shift power control and a direct managed by a comms system, are required when you don't have somewhere to spill the surplus power. So really this arrangement I've drawn here is somewhat a proprietary solution, not a generic solution, though frequency shift is becoming very common because of, in Australia and New Zealand, our inverter standard actually requires that mode to be available on grid tie inverters, that they have a frequency shift power control feature. So they will do it kind of anyway. And here at the Smart Energy Lab, I've been playing around with this for a long time. I've got 20 plus inverter systems connected to a microgrid, and they actually behave really quite well. Frequency shift does sort of keep them in check. Sometimes, you will hear a fair bit of frequency movement. 1.5 hertz doesn't sound much, but I notice my coffee machine runs a little bit faster when the frequency goes high. So, Rachel, how are we going on questions?
Oh, someone wants to know which brands of inverters are using comms cable for the control.
I'm probably not able to give you a full survey of that, but I'm certainly aware of Cellectronic. So Cellectronic, I have a setup here. In fact, it runs my microgrid, the new power chain system. I've got like 6 SP Pros connected to a 3-phase network, and they have both generic AC coupling, or which is frequency shift, or managed AC coupling. So we're just moving over to managed AC coupling now because of the large array being connected to it. So that's one system that I'm aware of.
Okay, and also Jijian Fu asks is the secondary protection required in an off-grid system?
Okay, so Jijian is probably referring to secondary protection covered in 4777 Part 1, which is the inverter standard in Australia and New Zealand for inverters connected to the grid. Part 2 is the design standard. Part 1 is installation. If you are interacting with a utility, you are affecting the safety and reliability of that system. And so they require, depending on the size of the system, what's called secondary protection, which is an independent isolating device that can isolate your system from their grid in case of power quality or safety issues. Off-grid, you are the utility. You do not need secondary protection. So the inverter, the battery inverter itself basically is the boss, and it determines what generates when.
Okay, another one is, which this, I think you may cover this in a minute. Well, Craig asks, would you also recommend a small DC coupled attached to the AC coupled in case your generator packs a SAD?
Yes, Craig, a man after my own heart. Actually, I might have a go at trying to draw this. This might be a little bit messy because I'm drawing with a mouse, but what Craig's referring to is sometimes called black start protection. Now, one of the problems with an AC coupled system, as I've drawn it here, is that if this battery system turns off because you've basically run out of power overnight and completely flattened that battery, that inverter will turn off. If that inverter turns off, the solar inverters don't have nothing to synchronize with. So even though in the morning the sun comes up, nothing's going to happen. So you actually got the sun sitting on solar panels connected to a solar inverter, and you have no power, and you have no way of charging that battery. And that's called a black start condition. Now, usually what you would rely on is a generating set. So a generating set comes along and it makes everything much better. So it comes along and starts up. And so we go, woohoo, automatic start generator or manually start generator. So the generator comes on, and that then provides AC power to the battery inverter, which wakes it up, which then wakes up the solar inverter. And we're back in action again. But Craig, I know you're an experienced installer. You probably know that generating sets aren't as reliable as solar inverters or solar panels, and there is always a reason they won't start. They've run out of fuel. The maintenance regime is insufficient. They've failed. The start battery has gone flat because it hasn't run for so long, and there's no trickle charge on that start battery. All of those things can mean your generator doesn't start. And this can be quite a big deal, which basically means a call out often for the installer to kickstart the system. But, and as Craig alluded, a simple solution is a small DC coupled system that connects to this that can directly charge that battery system independently of the generator or the solar inverter. So what I could do is put in a very small array, maybe just a couple of panels. So here's a small array that through a charge controller directly connects onto the battery and tops it up. Now, what that will mean is that if a black start condition were to occur, and particularly at nighttime, when the sun comes up in the morning, that little DC coupled system, now I haven't drawn a charge controller in there. I really should point out that you need some way of protecting that system from overcharging that battery. So that little thing there is a charge controller. So CC, gosh, it's hard to draw with the mouse. There we go. So a little charge controller. It will bring that battery up to a point, its voltage to a point where the battery inverter turns back on again. As soon as the battery inverter turns back on again, you're in action. And that means that if this turns on, then the solar inverter synchronizes with it and you're charging with full power again. So yes, Craig, I think it's a great idea to have a small black start protection in a system for reliability purposes. How are we going for questions?
Yeah, David Skelton just added to that, saying with an SP Pro, you still need fuel in the battery, storage in the battery to start the inverter, because at dead start he's saying that the generator will not reactivate it. Now, I understood that Selectronic have tried to make us create a solution for when the battery completely fails. So
yeah.
You can use an AC source to start it again, apparently. I don't know if that includes a generator.
So this actually is very much product specific, and David, you're correct. With the older firmware on the SP Pro, if the inverter turns off, now look, I'm not an agent for Selectronic, so anyone out there could correct me, but it won't turn on when the generator runs. You'll actually have to manually turn it back on again. But the new firmware, which I haven't tried out yet, has a sort of a special feature where it will protect itself from completely discharging that battery and save a little bit in reserve and try again later to start the inverter up. So chances are, after a few tries, it will hit it when the sun's shining and kickstart again. Some inverters actually will always charge the battery when there's an AC source. I know that this is a feature of Victron. So if there's an AC source available, they'll charge that battery, even if the battery is at 0 volts, like completely dead, which actually makes it quite useful for some interesting chemistries. You may be familiar with flow batteries. I've got a red flow system here at my lab, and they go through what's called a stripping cycle, and they will go down to 0 volts every so often as they basically rebirth themselves as a new battery. And during that time, there is no battery voltage, so the inverter can't see a battery. Victron solved that problem by allowing the inverter or the AC source to directly charge it.
Okay. This one from Nelson, I don't know what you mean, Nelson. Sorry, but it's doesn't that mean you have 2 chargers which do not have comms? And is that not also a problem?
Yes, thanks, Nelson. I understand what you're referring to. 2 chargers, as in you've got a battery inverter which can charge that battery, but you also might have a DC coupled system that can charge that battery. If they don't have any way of being sort of collaborating on what's the correct charge voltage to go to, a simple solution is just to set the lesser of the 2, which is most likely the black start protection DC coupled charge controller, to a lower voltage. So let's say it's a lead acid system, 48 volt lead acid battery, which might want to go to say 58.8 volts to absorption. You might set the black start protection system to cut out at 57 volts, for instance. So it's not going to overcharge that battery, and the battery inverter will always take control of the full charge cycle. But you do also need to consider, particularly with smaller systems, that you're not exceeding the charge capacity of that battery. So if you can put 100 amps in from the battery inverter and 100 amps in from the solar charger, you've got to consider it's possible that both of them could be running at the same time. All right, I'll go back to my presentation, let those questions accumulate again. Thank you. This is really helpful to have the Q&A window being managed by Rachel. Thank you for that. So here we are looking at that AC coupled system. So quite a lot of details gone into that, talking about different considerations. One more consideration I'd like to mention is the ratio that the solar inverter and battery inverter can be managed at. Now, this is always a proprietary decision, so you need to check with the manufacturer, but some AC coupled systems, the ratio is a maximum of 1:1. That means if you've got a 10 kilowatt solar inverter, you need a 10 kilowatt battery inverter for this to work. Others, particularly those that use managed AC coupling, they can sometimes have higher ratios, like 2:1, for instance, or even larger, because they know that they can control that solar inverter at very precise and very rapid timeframes. Now, let me show you something quite radical here, an off-grid system with no batteries. I did have a slide here with the pros and cons, which I've just gone through, I think. An important pro, which I forgot to mention, was that one of the big advantages of adding a battery inverter system to a generating set is that suddenly that generating set can be controlled at its optimum efficiency in terms of its demand from on the generator. So diesel generators, for instance, particularly larger ones, like a fairly constant load. You don't want to run a 25 kVA generator at 1 kVA. It's just going to glaze the bores, and it will use fuel very, very inefficiently. Many generators use almost the same amount of fuel no matter what load you've got on them. So you'll be wasting fuel. You'll be causing a high maintenance cycle on that generating set. But if you add a battery inverter that can charge batteries and supply loads in synchronization with that generating set, it will then run that generating set at the load that's most efficient. You program it into the inverter. So you might choose to run the gen set at, say, 75% of its maximum load, where the fuel efficiency is good, the maintenance cycles are low, and even if the batteries, if the loads are light, it will charge the batteries to maintain that load on the generating set. Or if the loads go up, it'll reduce the charge rate to the batteries and supply the loads. It also gives you the possibility where the battery inverter can parallel with another source, like a generator, to sum the two together. You might have a 10 kVA generator set and a 5 kVA inverter, but you can actually supply 15 kVA through to the loads because they can be synchronized together. So synchronizing sources. I think I've mentioned that one of the cons was that it does require communication. The other one is that you do need to consider the pass-through capabilities of that battery inverter if you're using the internal contactor. So many battery inverters with two ports, a generator port and a load port, have an internal contactor, and they might be rated something like 30 amps, 50 amps, 63 amps, 125 amps even. But if you're doing quite a big installation, you have to consider what is the maximum pass-through capability for when the generator is running and the loads are drawing very, very high current. Some battery inverters allow external contactors to be installed as well, so the limit's almost the sky. On my system here, I think I've got a 250 amp contactor on the output, so I could run a ridiculously large load for what is effectively a small microgrid of 7 homes. Now, I did say I'd talk about no battery. So this is what's known as a diesel-solar hybrid. It is a bit of a narrow use case. It's probably more typical of a off-grid industrial site, something like a mining site, where that generating set is continuous power. It's not designed to turn off. It's running all the time. But it is possible to add some renewables into that mixture. And here we've got a solar inverter in parallel with that generating set. Because solar inverters have a special power, which is they can synchronize with another source. So they'll see the generator's frequency and monitor it. They'll match it internally before they parallel with it. So they're watching the frequency and voltage. They synchronize on the 0 volt crossover point, close their paralleling contactor, and work in unison with it. And then they can start to flow power in the reverse direction back towards the load center. But generators don't like reverse power. Unfortunately, you can't feed power into a generator and make diesel. It's a one-way device. So you need some form of reverse power protection in a design like this that may be built into the generating set. Many quality generating sets have reverse power protection as standard, but it may be a standalone product that ensures that you don't backfeed a generator and cause it to stall or even fail. So that is a little bit of an unusual one, but more likely a commercial off-grid site. So Rachel, how are we going on those questions?
Yeah, I was just writing an answer, but seeing you're here.
I'm still here.
Glenn's thoughts, it's an anonymous. Hello, anonymous. Glenn's thoughts on cost benefit of AC coupled versus DC coupled. Seems strange to buy 2 inverters in an AC system where a DC system only uses 1.
So anonymous, I wish I actually had a slide for this. There is in terms of the economics, a kind of a point at which DC coupling is a better choice. Now, I'd say you don't want to put in your RV an AC coupled system. Basically, there'd be nowhere to sit in the vehicle because you'd have 2 inverters in the back seat. So very small systems, pure DC coupling makes a lot of sense. So a DC coupled system with a charge controller can be as small as a packet of cigarettes, just a tiny little box. So they're very compact. They're also very, very efficient. Not much heat's given off by them, so they don't often have any cooling fans, and they're ideally suited to directly supplying a battery from a PV module. But that sort of scale starts to peter out in terms of cost efficiency. I don't know, around a 2 or 3 kilowatt mark of PV, I'd start to think that I'd be moving to AC coupling. And that's partly because of the limitations of most charge controllers. DC charge controllers historically had quite low maximum input voltages, up to around about 150 volts. These days, there are a few that go beyond that now. We're starting to see 250 volts, 300, and a few even at 600 or 750 volts, but very, very few, only 1 or 2. But at those lower voltages, I say 150 volts maximum, you're restricted to more or less 2 or 3 panels in series. And to build a larger system, you're going to have quite a lot of parallel strings. Now, you might go, what does that matter? Parallel strings, just, more cables joined together. Well, if you happen to live in New Zealand or Australia, our PV array standard, ASN ZS5033, requires string overcurrent protection, where there is a possibility in a multi-string system to thermally damage the cables in other strings. And that means basically putting fuses in both poles of every string. And that starts to add cost, complexity, and you need more enclosures. Also, your currents start to get really big as you build a bigger system. I mean, if you're doing a 12-volt system, once you get to a kilowatt of panels, you've got a lot of current. So using Ohm's law, you divide the power by the voltage and you can work out what the current is. So current becomes your enemy. I mean, my personal experience is at one point on my home here, I had a system which had 54 strings. Now, it wasn't a huge system. Unfortunately, I had a lot of thin film modules, and every one of them was a 100-volt module. So I had to have one module, one string. I don't know if Rachel remembers that one, but yeah, we ended up with a lot of strings, a lot of string fusing, and so the economics don't make sense for a DC coupled system generally. So I'd say once you get to 2 or 3 kilowatts, AC coupling starts to have an advantage. But there is still a use case for large DC coupled systems, and that would be, say, a telecommunication site where you have a fairly constant load. Your load might be a transmitter, which draws 2 kilowatts, but it's drawing 2 kilowatts 24 hours a day. So you might need a 2 kilowatt inverter to run the transmitter, but you need to put in a lot of renewable energy into that system. 2 kilowatts times 24 hours a day is 48 kilowatt hours. So, it's going to be a 10 or 20 kilowatt PV array to produce enough energy, depending where you are, to keep that system running. So suddenly you need a very big solar charging system. Now, with DC coupling, you can spend the money on the DC chargers, not having to match that with the inverter. So with an AC coupled system, if I've got 20 kilowatts of solar inverters, I need 20 kilowatts of battery inverter to accept that power. So that's kind of a narrow use case, but still valid, where DC coupling on larger systems makes sense. And of course, you can do both. You can have AC and DC coupling, whether it's an upgrade, black start protection, or just more robust design. What have you got for me?
Okay, well, there's a couple that are unrelated. One goes back to the review of standards, and Matthew Carmichael asked about 4509. It's been less than 10 years, but design principles established prior to newer battery technologies.
Okay, so ASNZS 4509 was really last edited back before 2000. I think around about we started it back about 1999, and so it got published in 2007 and 2010 in 2 parts: the design standard and install standard, and they were written really in the days before AC coupling had really taken off. So they don't fully recognize the benefits of AC coupling, nor do they model them that particularly well. But apart from that, actually, it's still an excellent standard for design principles. So I still teach it as my primary document for designing a standalone power system. What I have done, and Matt probably knows about this, is I've dumbed it down a whole lot. It was written at a time when solar was very expensive. And so it was about very precise calculations to work out how much PV you need. These days, it's think of a number and double it. Just put lots of PV on to cover all those sins of, not enough allowance for growth in usage, best day, worst day combinations, and generally just keeping the cost of the battery system down, because the bigger your PV array is, the less chance you'll even need to use your batteries during the daytime. It'll only be there for nighttime loads. So oversizing solar has really been a pretty common feature of systems in Australia and New Zealand because of the cost structure of PV, but 4509 doesn't really model that.
Okay, Glenn, just an easy question. Can you tell me what your YouTube channel's called, please?
So,
I can answer this question.
Yeah. What is it, Rachel?
I think it's Smart Energy Lab.
Correct. So just go to YouTube and search for Smart Energy Lab, and you'll find me there. This series is the latest that I've been uploading every day. Each of these sessions are recorded and uploaded in the afternoon with a little bit of editing to remove some of the glitches. But you'll find a lot of interviews there with industry people. So when I go to trade shows, for instance, I take my camera set with me and I just do little interviews with people who sell products. So it's a way of taking you on a virtual conference tour. And plus I do some reviews of products here at the Smart Energy Lab. So that's one of the things that I do is field testing of products. I'm very fortunate. A lot of companies support me with sending me product and try it out. It also means my students get to be trained on contemporary products and can give feedback on new and evolving products even before they hit the market. So yeah, Smart Energy Lab, you'll find me on YouTube. That was a nice, easy one.
Yeah. Okay, and there is an essay here, but it may be for another day from Jerry Tumer about a three-phase trial for voltage regulation by the distributor.
Okay. Jerry, I don't want to brush off these more in-depth questions. What I do is these get saved and I review them, and I may well use this as part of another webinar series, because really this is an introductory level series for people in the solar industry, but there is always those side issues, and I think you've probably got quite an interesting topic there. So I'll review this one and maybe come back to it. So let me jump back into my presentation now, Rachel. So we talked about a batteryless system where we basically got an off-grid site, probably a commercial or industrial site that runs a generating set continuously. The pros in this is that solar helps support the generator's output. So the main benefit may be that the peak demand correlates with the sun. So you may have heavy daytime loads, and the generating set can be somewhat undersized as long as that solar is fairly reliable. So you're probably thinking not a coastal area where the clouds come in all the time. But the cons are that you will actually reduce demand on the gen set where fuel consumption might be poor. So unless you've got a low load designed generating set that's designed to run at low loads, too much renewables in this situation can actually lead to poor fuel efficiency on that generating set. So what I want to move on to now is a bit about understanding customers' loads and batteries and generation together. So these two slides I'm going to run through is trying to explain, and this is applicable for a hybrid system. It's a little bit different for off-grid. So sorry, actually this slide's probably more applicable for hybrid, but the same principles apply. You'll notice that the blue area is the load energy. Now, getting data about customers' loads, for those who have done my 4-day course here at the Smart Energy Lab will know that I bang on about loads a lot. I say that actually the hardest part of designing a system is to find out what the problem is. What are you trying to produce a system for? I mean, customers have a simple understanding often. They'll say, oh, look, I've got a 2 to 3 bedroom home. How much is it going to cost me? You roll your eyes and go, well, okay, let's just start with what's going to be in that home. It's all about the loads. And it can be the kilowatt hour demand. That's one part of it, the load energy that you need to produce enough renewables over a day or even a bad day for, or a bad month. But it's also the peak demand. How high are those peaks? Well, the coincidental peaks. And I've crudely drawn this chart here, but when you look at real load data, it's very digital. Things just turn on and off. Your toaster doesn't slowly ramp up in power. It comes on at 1500 watts, it turns off at 0. It doesn't ramp up slowly. And so you'll see, model a lot of homes, including my own. In the morning, you'll see all these little spikes, the coffee machine, the toaster, the dishwasher, they just spike, spike, spike. And they can be coincidental spikes, particularly natural coincidences, like anything that washes, that heats water, is probably going to run a pump if you've got a pressure pump. So they both come on together. Now, those peaks are going to be delivered by your inverter system. So both your battery and your inverter need to be sized to deliver that peak demand. And your PV system needs to be sized to give the energy requirement over the whole day. Now, there's some optimizations that can be made in a design, whether it's on-grid or off-grid, which is trying to get loads to occur when the sun is shining. Now, it seems really kind of obvious, but if you can control loads in any way, so you can schedule them, or you've got some digital controls for those, and try to get them to operate in the middle of the day, that means you're not storing that energy in a battery for later use. So having controlled loads is a real bonus. What's been happening with the solar industry over the last decade or so is there's been more smarts being put into appliances, and a lot of equipment is starting to talk to other equipment. So we're seeing this term smart energy pop up. Basically, appliances that can be controlled, generating sources and storage that can interact in a smart way. That might be a controller, might be the inverter. It might be a standalone product that actually talks to and monitors and controls all those things. And that ability to do all the thinking for you is a big plus. Something that knows when you need hot water, knows when there is surplus solar and the battery's empty, knows when to turn on a load because the battery's full, but the sun is shining. So controlled loads help fill in that orange area in this chart. So the orange area above the black line is basically surplus solar energy that has to be stored or worse still, curtailed or not produced. In the evening, we've got a load that comes on, and I've shown here that the battery energy cuts out at 3 kilowatts. Now, this would mean you would need a generator, because if your loads go to 6 kilowatts, but your inverter can only deliver 3, you're going to have a generator set to parallel with it. So whether it's paralleling or it switches over, that's another option. It's not so common anymore, but in the day when I first went off-grid back in 1991, we just basically had a changeover switch. We'd turn the house over to generator only or inverter only. But because of modern power electronics, it's now possible to parallel that inverter with the generating set. And often the generating set will control that starting process. So as the loads ramp up in the early evening, they get up to say 2.5, maybe 3 kilowatts. The inverter goes, whoa, I can't keep this up for much longer. I'm getting hot. And I'll call upon the generator for help. And so the generator will come online and fill in the top half of that blue spike in the evening. So that's all part of understanding the loads. And getting this information, as I said at the beginning, is the hardest part in the design. I'd suggest that you don't make any simple predictions. You ask for evidence. Like I usually give the customer a load sheet to complete, and I say, can you please list the loads you want this design to meet? Can you tell me what those appliances are? If you know their power ratings and their hours of use, can you put them in here too? And we can use that to base our design on. And from a kind of legal perspective, if you ever get into trouble, the customer goes bad on you and you end up in court, having evidence of a design is really, really valuable. Okay, so Rachel, we've got any good questions come through?
Yes, we have 2 good questions. One's from Tino. And he asks if he had a greater than 500 kilowatt solar PV system, and on some occasional days when sunshine level falls intermittently, why are generators slow or struggling to respond to the demand?
Okay, actually struggling slight to understand the question. So you've got a large PV system. Oh, so this is a microgrid system, I presume, because you're from the Cook Islands. You've probably lived on a microgrid, and you've got a large permanently operating generating set with PV as well, and a cloud comes over and suddenly the PV disappears and the generating set struggles to meet that load. Well, it's really just the inertia of that generating set to ramp up its power output fast enough. They're not as fast as a battery and an inverter. They do actually have to, open their throttles basically and increase their power output to meet that load requirement. So it is a challenge when you have very spiky loads. Every load has its kind of special characteristics, and generally a microgrid means that you smooth out a lot of those spikes because they don't the coincidental loads aren't so coincidental, and more like, house number 1 turns the coffee machine on, house number 2 does, house number 3 does, and it's just ramping up nicely. But occasionally you have the Coronation Street problem. For those of you from the UK probably have heard of this one. People who watched a TV program like Coronation Street in the UK, as soon as the ad break came on, would rush and turn the kettle on. So the whole of the UK would turn their kettles on at the same moment. And the power station operators would be sitting there watching Coronation Street, not because they were bored, but because they had to be ready for it. When that ad break came on, they knew that there would be a spike in demand. So sometimes with microgrids, you've got that same problem. You may have some coincidental event like everyone goes to church at the same time. Everyone turns their power off or comes home at the same time. So those things are definitely a bit of an issue in the design. Any other questions?
Thank you, Glenn. I like that question. Fabio asks, which equipment do you recommend to detect load surge power, and which sampling rate should I have? 10 millisecond, 5 second, etc.
Well, I presume that you mean detect a load surge and respond to it to protect equipment. So really, the speed of that surge protection needs to be suitable for the protection required. So if you've got circuit breakers that could trip, you can look at the time current characteristic of a circuit breaker to see how long it can operate at a certain point, which normally correlates with the cables that it protects. If you've got generating equipment such as reverse power considerations, how fast does that response time need to be? So really the response time is determined by what you're trying to protect.
Our standards 5139 and 5033 call for string overcurrent protection. Can this be provided only by a fuse switch, like a rat trap, or by an isolator circuit breaker, which is suitable for isolation?
So Anonymous, excellent question. And I think this is actually subject I'll cover in more detail in a subsequent webinar, but I'll give you a very brief answer. You can use anything suitable for overcurrent protection, but it needs to be suitable for the characteristic of the source. And in the case of PV, it's kind of weird. The solar panel doesn't have a high prospective fault current. If you short circuit a PV panel, its output's only about 5 or 6% more. So your discretion for protection is very, very narrow. That makes circuit breakers generally not suitable. There are a special class of fuses, classes called GPV, which are designed for a relatively low overload condition. And the standard itself specifies what the multiplier should be. So if you do trigger the requirement for string overcurrent protection, the protection should be at least 1.45 times the short circuit current, and no more than 2.4 times the short circuit current, and no more the reverse current rating of the string or the module. So that's why it's actually a subject for another webinar. It's a little bit complicated, and it's probably one of the most asked questions I get from installers. So thanks very much for that one, and I will cover it in detail. Now I've got a couple more slides to go through, I think, or one more. So I'll just go back to that now, if you don't mind. So here we are, the same slide I'll just show you. That's what we were looking at before. We're talking about load characteristics. But the next one is slight variation. I've added a red line to show the state of charge of a battery storage system. Now, if you're designing a solar PV system, you've got two considerations in sizing. Well, really three. You've got how big's your PV, how many kilowatts of PV or watts of PV you've got, how much storage have you got in terms of kilowatt hours of energy can you store in the battery, and also what's the rating, the power rating of the inverter. So let's just drop the inverter out of this equation. I'm mostly concerned about the ratio of the PV power to the battery storage. If you have insufficient PV to fully charge a battery on a good day, you're never going to charge that battery fully from a renewable source. So you're undersized in your battery. So you need to consider the solar resource and the amount of energy that it can capture for your design month, and make sure the battery system is going to be fully charged. Now, it's not always critical to fully charge some battery chemistries. I should make that point. For instance, lithium batteries really aren't that fussed. If you charge them 50, 60% and then discharge them again, they don't mind. In fact, Lithium is a little bit different. They actually don't like to be sitting on full charge all the time. They like to be a little bit less than that because it builds up pressure inside the cell. But any cycled system will drop that every day, so it's not a problem. But with lead acid, you're actually trying to charge the battery for a chemical reason to reverse the damaging effects of sulfation. So a lead acid battery needs to be fully charged to protect it from what's known as sulfation on a regular basis. Ideally every day, but at least every few days. If you don't do that, and so you've undersized your PV and your battery's bouncing along all winter because it's only going to get fully charged in summer, you would damage a lead acid battery. And it's one of the most common reasons for failure is what's called partial state of charge cycling, not letting a lead acid battery fully charge. You might have a reverse problem is your PV is way too big and your battery is fully charged, in this case, by 1 o'clock in the afternoon. Now, it's actually not a problem. You could say it's a good problem to have because, as I said before, oversizing a PV system gives you a lot of flexibility for change in demand, so the customer starts to use more energy as time goes by. And on less than ideal days, you're still getting a large amount of renewable energy input. So oversizing, not a design problem, maybe just a cost consideration, but undersizing of your storage, of your solar compared to your storage is a performance issue. And unless you're prepared to use a generating set to finish that charging process, you may damage particularly some chemistries like lead acid. Now, we've only got about a minute to go, so a couple of minutes to go. So let's just see if there's any more questions there, Rachel.
Yeah, there's a couple here, Glenn. I think there'll probably be a few rapid fire ones now, but we'll just see how we go. So Fabio just wanted to clarify when he was asking about detecting load surge power, and he's asking about how fast does he have to sample the load to catch the spike?
Okay. Yeah. So you're using a device for analyzing the load. Well, it's sort of the same answer in a way. If there is some piece of equipment that can be damaged by a spike at a certain rate, your sampling needs to be as good as that. But in practice,
asking if it's should he use an oscilloscope? I know how to say that. Sorry.
Yes, you could use an oscilloscope with capture turned on, so it captures those peaks. That would be very fast. They're megahertz, so you'll capture everything. But if you're using just a data logger, often they've got, I've got a couple of data loggers here. They're often, the resolution only goes down to 1 second. So I can't see sub-second spikes. But it just depends on, once again, what you're trying to protect. Okay, next question.
I think, well, okay, we'll go through these quickly. There's a comment, someone, Rani, I'm not sure if Glenn will answer this, but he's familiar, Rani's familiar with the SMA Sunny Home Manager that does this to a seemingly good degree. Now, this was about 7 minutes ago, so I'm not sure what you would, and optimizes self-consumption if that's what the end user wants. Do you know about
Okay.
Brand?
I'll have a go at answering that one, Rachel. So thanks, Rani. Full disclosure here, I don't have a Sunny Home Manager in the lab, so I haven't had experience with one, but I do know about them. There are similar products. Basically, it's a smart device that can interact with generation and storage systems to optimize control of loads and matching that to sources of energy, whether it's battery energy or solar. And like I said earlier on, really smart energy is the future when it comes to giving the best outcomes for performance and reliability and even cost of operating a system. So that's about all I can say on that one. Rani? Okay,
David, what adjustments do you need for selling your extra power from solar panels back to the grid?
Okay, so this today's topic was predominantly really off-grid, so there is no grid to sell it to. You are the grid operator if you're off-grid. It could be a standalone system or it could be a microgrid system. I run a small microgrid here at my lab. There's 7 homes connected to it. I don't charge anyone for the power that goes back to their homes. I'm learning by doing, so I get a benefit from having them as a load and generation source. But if you are connected to the grid, the settings really are determined by the approvals for connecting, and you may have export limiting requirements. if you don't have export limiting, basically a solar inverter will spill power back to the grid whenever it can when the loads won't consume them. I think we've got time for one more question. Oh no, it's 12 o'clock. Okay, we actually have run out of time. I'm trying to be strict on the time here because I know people often have another Zoom meeting to go to, so I don't want to run over time. So today we looked at off-grid systems, and the day before was hybrid systems. We're getting deeper each topic. So tomorrow we're going deeper. I actually haven't fully reviewed it because I'm looking at some of the comments that came in today, so I might tweak that. So hopefully I'll see you back tomorrow at the same time. And thank you once again to Rachel for your assistance in moderating all these comments.
There's a question here you're going to want to answer.
Okay, go for it. Bonus.
Fabio again. If I have an off-grid system with an MEN link in the MSB in the home and genset and inverter battery installed in the shed 200 metres away, all items wired in a local distribution board, should I remove the MEN in the MSB and have it in the shed distribution board?
So if you're in Australia or New Zealand, you're covered by AS3000, and the principles of AS3000 apply off-grid as well, which is there's only one link between neutral and earth in a system. It must occur at the main switchboard. For instance, if you have a generating set connected to an inverter, many generators come with an inbuilt MEN because they're designed to be a standalone power system for site use. That actually needs to be removed. Your protection equipment, your RCDs won't operate safely with multiple MEN points. So that MEN must be in the main switchboard, and that must be identified, and that's where your earth stake will connect. So thanks, everyone. I hope that satisfied Fabio. Got some good questions there, and I'll see you all again tomorrow. Thanks for attending today's session. Tomorrow, we're going to be looking at off-grid systems and understanding the system configuration options from single line diagrams through to understanding the difference between generation and load and the importance of combining a design that considers both. Looking forward to it. See you tomorrow.